world where it rains diamonds, where a storm the size of Earth erupts once every 30 years and wraps itself around the entire planet. Where a hexagon made of wind, wider than two Earths placed side by side, has been spinning at the North Pole for centuries, and nobody fully understands why. Saturn, beautiful, hypnotic, and deeply, deeply wrong. Beneath those golden clouds lies an interior so extreme that hydrogen stops being a gas and becomes a liquid metal. A core so diffuse, so smeared into the layers above it, that scientists cannot even agree whether it is solid or simply a gradient of pressure dissolving rock into oblivion. The rings, those iconic bands of ice that define the planet in every textbook, every poster, every child's drawing of the solar system, are dying, falling into Saturn like rain. Gone, perhaps, in less than 100 million years, a cosmic blink. And then there are the moons, 146 confirmed worlds orbiting this giant. One of them, Titan, has lakes of liquid methane and an atmosphere thicker than Earth's. Another, Enceladus, is shooting geysers of salt water into space from an ocean hidden beneath miles of ice, an ocean with hydrothermal vents, organic molecules, and conditions that look disturbingly similar to the places where life first appeared on our own planet. Saturn is not just a planet, it is a system, a kingdom, and its story, from violent birth to slow, inevitable death, is one of the most extraordinary tales in all of science. But before we begin, if you enjoy these nighttime journeys, remember to like and subscribe. It helps us bringing you more videos like this. Now, let us begin. Chapter 1. The Birth of Saturn. How a Giant Claimed Its Throne. 4.5 billion years ago, there was no Saturn, there was no Earth, there were no planets at all. There was only a cloud. A vast, slowly rotating cloud of gas and dust, hanging in the arm of a young galaxy, collapsing under its own gravity. At its center, temperatures climbed, pressure built, and then ignition. A new star flared to life, our Sunday. Around that infant star, the leftover material did not simply vanish, it flattened into a disk, a spinning platter of hydrogen, helium, and heavier elements forged in the depths of older stars. Iron, silicon, carbon, oxygen, water ice, all of it swirling in a structure astronomers call a protoplanetary disk. And within that disk, the raw ingredients for everything we know began to clump together. Grain by grain, pebble by pebble, rock by rock. Close to the sun, where temperatures were high, only metals and silicates could survive the heat. That is where the rocky planets formed: Mercury, Venus, Earth, Mars. Small, dense, baked by radiation. But farther out, beyond a boundary scientists call the frost line, roughly where the orbit of Jupiter sits today, the temperature dropped enough for water ice to exist as a solid, and ice was everywhere. This changed everything. Beyond the frost line, the building blocks of planets were not just rock, they were rock and ice combined. And ice was abundant, far more abundant than metal or silicate. The cores forming out there could grow larger, faster, pulling in more material with every pass around the young Sunday. When a core reached roughly 10 Earth masses, something dramatic happened. It crossed a threshold. Its gravity became strong enough to capture not just solids but gas. Hydrogen and helium, the lightest and most plentiful elements in the disk, began to fall onto the core in torrents. This is how a gas giant is born. Not gently, not gradually, but in a runaway process that can double and triple a planet's mass in a cosmically short span. The core acts like a seed. The gas acts like a flood, and once that flood begins, it does not stop until the supply runs out or the disk itself disperses. Saturn formed this way. So did Jupiter. But their stories are not identical, and the differences matter enormously. Jupiter formed first. It was closer to the frost line, where material was densest. It grew fast, became massive, and began to dominate the gravitational landscape of the outer solar system before Saturn had finished assembling. Jupiter today holds roughly 318 Earth masses. Saturn holds roughly 95. That gap is not an accident. Jupiter got to the buffet first and took the largest share. Saturn arrived second and had to work with what remained. But Saturn did something Jupiter could not. It kept growing its core while accumulating a proportionally thicker envelope of gas relative to its total mass. The result is a planet with a fundamentally different internal structure. Saturn is less dense than Jupiter. In fact, Saturn is less dense than water. If you could find an ocean large enough, Saturn would float. That single fact, absurd as it sounds, tells you something profound about how this planet is built. It is mostly hydrogen and helium, puffed up, distended, a balloon of gas surrounding a core that may not even be solid anymore. The early solar system was not a peaceful place. The planets did not form in their current orbits and politely stay put. They moved, they migrated, they fought for position in a gravitational contest that nearly destroyed everything. The best model scientists have for this chaotic period is called the Nice model, named after the city in France where it was first developed by Alessandro Morbidelli, Rodney Gomes, Cleomenes Tsiganis, and Harold Leveson. Published as a series of landmark papers in the journal Nature in 2005, the Nice model proposes that Jupiter, Saturn, Uranus, and Neptune originally formed much closer together than they are now, packed into a compact configuration between roughly 5.5 and 17 astronomical units from the Sunday. Beyond them lay a massive disk of icy planetesimals, small bodies left over from the planet-building process. For hundreds of millions of years, this arrangement held. The planets orbited quietly, the planetesimal disk sat undisturbed. And then, the balance broke. Jupiter and Saturn drifted into what physicists call a 2-to-1 mean motion resonance. For every 2 orbits Jupiter completed, Saturn completed exactly 1. This orbital lockstep amplified gravitational interactions between the 2 giants. The effects cascaded outward. Uranus and Neptune were kicked onto wider, more eccentric orbits. One of them, possibly Neptune, plowed through the outer planetesimal disk like a bowling ball through pins. The result was catastrophic. Billions of icy bodies were scattered in every direction. Some were flung outward, forming what we now call the Kuiper belt and the Oort cloud. Others were hurled inward, bombarding the rocky planets in a devastating barrage that scientists once called the Late Heavy Bombardment. The craters you see on the Moon, the scars on Mercury, the ancient impact basins on Mars, many of them may trace back to this single event. A gravitational tantrum triggered by the dance of Jupiter and Saturn. There is even evidence, from computer simulations run by David Nesvorny at the Southwest Research Institute, that the early solar system may have contained a 5th giant planet, an additional ice giant roughly the size of Neptune that was ejected entirely from the solar system during this instability, thrown out into interstellar space. A rogue planet, wandering the galaxy in darkness, because Jupiter and Saturn rearranged the neighborhood. Saturn survived this chaos, but survival came with consequences. Its final orbit, roughly 9.5 astronomical units from the Sun, was not the orbit it was born into. It had been pushed outward, nudged by the same gravitational interactions that scattered everything else. The tilt of its axis, roughly 27 degrees, was likely influenced by these early encounters. The collection of moons it would eventually gather, some captured, some formed from debris, bears the fingerprints of this violent reshuffling. Think about that for a moment. The Saturn we see today, serene and golden and impossibly beautiful through a telescope, is a survivor of a war. A war fought not with weapons but with gravity. A war in which entire worlds were destroyed or expelled, A war that shaped every orbit, every moon, every ring in the solar system. Saturn did not inherit its throne peacefully. It claimed it through a process of gravitational natural selection. The planets that could not adapt were swallowed, ejected, or broken apart. Saturn endured. And it endured with a secret. Something hidden beneath those calm, banded clouds. Something scientists would not begin to understand until a spacecraft named Cassini arrived at Saturn in 2004 and started peeling back the layers. What Cassini found was not what anyone expected. The planet's interior was stranger, more complex, and more unsettling than any model had predicted. The core was not a neat ball of rock and ice sitting at the center like a pit inside a peach. It was smeared, diffuse, a gradient of heavy elements dissolving upward into the hydrogen and helium envelope, extending outward to roughly 60% of the planet's radius. Scientists now call this a fuzzy core, not solid. Not liquid, not gas, something in between, something that defies easy categorization. Christopher Mankiewicz and Jim Fuller at the California Institute of Technology discovered this by studying waves in Saturn's rings. The planet quivers. It oscillates like a bell being struck, and those oscillations create patterns in the innermost rings that act like a seismograph. By reading the rings, Mankiewicz and Fuller could peer inside the planet in a way no probe had ever achieved. What they saw was a core containing roughly 55 Earth masses of material, 17 of which were rock and ice, the rest hydrogen and helium, all of it layered, all of it sloshing, all of it fundamentally different from the tidy, solid cores that textbooks had described for decades. This discovery did not just change our understanding of Saturn, it changed our understanding of all giant planets. If Saturn's core is fuzzy, perhaps Jupiter's is too. Perhaps every gas giant in every solar system across the galaxy formed this way, not with a clean separation between core and envelope, but with a messy, gradual transition that reflects the chaotic, turbulent process of planet formation itself. Saturn was born in violence. It survived through gravitational luck and sheer mass, and it carries within it a structure so strange that even after decades of study, scientists are still arguing about what it means. But the interior is only the beginning. The most recognizable feature of Saturn, the feature that makes it the most iconic planet in the solar system, is not hidden inside. It orbits outside, visible, stunning, and as we are about to discover, deeply disturbing. The rings of Saturn are not what they seem. They are not ancient, they are not permanent, and their origin may involve something far more violent than anyone imagined. Chapter 2: The Rings, a planetary murder scene. In 1610, Galileo Galilei pointed his telescope at Saturn and saw something he could not explain. The planet appeared to have ears. Two blurry lumps flanking its disk, visible but unresolvable through the crude optics of the time. He drew them as handles. He wrote letters describing what he thought might be two large moons pressed close to the planet's sides. 2 years later, when he looked again, the lumps had vanished. Saturn appeared perfectly round. Galileo was baffled. He reportedly asked whether Saturn had devoured its own children, a reference to the Greek myth of Kronos, the titan who ate his sons. He never solved the mystery. It would take another 45 years before Christiaan Huygens, a Dutch astronomer with better instruments, correctly identified the structures as a flat ring encircling the planet, but not touching it. And it would take another 2 centuries before James Clerk Maxwell, the Scottish physicist, proved mathematically that the ring could not be solid. It had to be made of countless individual particles, each orbiting Saturn independently. Maxwell was right. We now know that Saturn's rings are composed of trillions upon trillions of pieces of water ice, ranging from grains smaller than sand to chunks as large as houses. Some are clear as glass. Some are dusted with organic compounds, and silicate impurities. Together, they form a structure roughly 175,000 miles across, but staggeringly thin, often no more than 30 feet from top to bottom. If you scaled Saturn's rings down to the diameter of a football field, they would be thinner than a razor blade. The rings are divided into named sections. The broad, bright B ring is the densest and most massive. The A ring sits outside it, separated by the Cassini division, a gap roughly 3,000 miles wide, first identified by Giovanni Domenico Cassini in 1675. Inside the B ring lies the faint, translucent C ring, sometimes called the crepe ring. Farther in still is the nearly invisible D ring, grazing Saturn's cloud tops. And beyond the main rings, far out, lies the enormous E ring, a diffuse halo of tiny ice particles fed by geysers erupting from the moon Enceladus. For most of the 20th century, scientists assumed the rings were as old as Saturn itself, 4.5 billion years old, relics of the solar system's formation, leftover material that never coalesced into a moon because it orbited too close to the planet, inside a boundary called the Roche limit. The Roche limit. This is one of the most important concepts in planetary science, and one of the most unsettling. Named after Edouard Roche, the French astronomer who calculated it in 1848, the Roche limit is the distance from a planet within which tidal forces, the difference in gravitational pull between the near side and far side of an orbiting body, exceed the body's own internal gravity holding it together. Cross inside the Roche limit and you get torn apart. The math is elegant. The Roche limit depends on the densities of both the planet and the orbiting body. For Saturn, with its relatively low density, the classical Roche limit for an icy body sits at roughly 2.5 Saturn radii from the planet's center. Saturn's main rings lie almost entirely within this boundary. That is not a coincidence. Inside this invisible line of destruction, no moon can hold itself together by gravity alone. Ice and rock that wander too close are shredded into fragments. Those fragments spread out, collide gently, and settle into the thin disk we see today. Every planet has a Roche limit. Earth has one. Jupiter has one. Even our moon would be torn apart if it somehow spiraled close enough to Earth. The concept is universal. But on Saturn, the Roche limit is not a theoretical curiosity. It is an active process. It is the mechanism that created, maintains, and is slowly destroying the most beautiful structure in the solar system. And here is where the story takes its dark turn. The rings are young. This was the bombshell that emerged from data collected by the Cassini spacecraft, which orbited Saturn from 2004 until 2017. During its grand finale, a series of 22 daring orbits that threaded the gap between Saturn and its innermost ring, Cassini measured two critical quantities. First, the mass of the rings. Second, the rate at which cosmic dust from interplanetary space accumulates on them is less than #0. 5 is greater than. The mass came in surprisingly low. About 40% the mass of the moon, Mimas, Saturn's smallest major moon. That is roughly half the mass of the entire ring system, earlier estimates had suggested. A lower mass means the rings have less inertia, less ability to resist change, less resilience against the forces eroding them. The dust measurement was equally revealing. Sascha Kempf, a physicist at the University of Colorado Boulder, led a team that analyzed data from Cassini's cosmic dust analyzer. They calculated how much interplanetary grime settles onto the rings each year. The answer was tiny, less than a gram per square foot annually. But over billions of years, even a sprinkle adds up. If the rings were truly 4.5 billion years old, they should be filthy, darkened by eons of accumulated debris. Instead, they are strikingly bright. Almost pure white water ice, clean as fresh snow. Think about it like a white carpet. Lay it down in a house and wait. Dust settles, dirt tracks in, stains appear. The longer the carpet has been down, the dirtier it gets. Saturn's rings are that carpet, and they look brand new. Kempf's study, published in the journal Science Advances in 2023, concluded that Saturn's rings are no more than 400 million years old. Other analyses using Cassini data push the estimate even younger, perhaps as low as 10 million to 100 million years. That means the rings formed long after Saturn itself, long after the chaos of the early solar system had settled, long after the planets had reached their current orbits. In geological terms, Saturn acquired its rings recently. Dinosaurs may have already been walking the Earth when Saturn's rings appeared. This raises an obvious question. If the rings are not leftovers from Saturn's birth, what created them? Something was destroyed. The leading hypothesis, supported by supercomputer simulations run by Jacob Kegerais at NASA's Ames Research Center and published in 2023, is that the rings formed from the debris of a catastrophic collision between two of Saturn's icy moons. The simulation modeled nearly 200 different collision scenarios, varying the size, speed, and angle of impact between precursor moons. In many cases, the collisions produced exactly the right amount of icy debris inside Saturn's Roche limit, where tidal forces would then spread it into the thin disk we observe today. The trigger for the collision may have been an orbital resonance with the Sunday. Saturn's moons slowly migrate outward from the planet over time, pushed by tidal interactions. As they move, some pass through orbital zones where the Sun's gravity creates a cumulative, destabilizing effect, a resonance that elongates and tilts their orbits until paths cross and impact becomes inevitable. Saturn's moon Rhea currently orbits just beyond one of these resonance zones. If Rhea were older and had been migrating for billions of years, it would have crossed the danger zone in the relatively recent past. The implication is staggering. Saturn's rings are not primordial beauty. They are the remains of a murder. A moon, possibly two moons, shattered by collision, their ice and rock scattered into orbit around the planet, where tidal forces inside the Roche limit ground the debris into the thin, luminous disk we see today. The rings are a crime scene, and the evidence is still falling. Because the rings are not just young, they are dying. James O'Donoghue, a planetary scientist at NASA's Goddard Space Flight Center, led research published in the journal Icarus, confirming that Saturn is losing its rings at what he called the worst-case scenario rate. Ice particles in the rings become electrically charged by ultraviolet radiation from the Sun or by impacts from micrometeoroids. Once charged, these particles respond to Saturn's magnetic field. They slide along invisible magnetic field lines and fall into the planet's atmosphere at mid-latitudes, a process scientists call ring rain. The numbers are sobering. Ring rain alone drains enough water to fill an Olympic-sized swimming pool every 30 minutes. Add the equatorial infall measured by Cassini during its grand finale, material spiraling directly into Saturn's equator under the combined influence of gravity and drag, and the total loss rate climbs dramatically. At this pace, the entire ring system could be gone in less than 100 million years, possibly much sooner. 100 million years sounds like a long time. It is not on the scale of the solar system. Saturn is 4.5 billion years old. 100 million years is roughly 2% of its total lifespan. We are witnessing the rings during a brief, shimmering window, a window that opened recently and will close permanently. Future civilizations, if they exist, may look at Saturn and see nothing but a plain, banded gas giant, indistinguishable from a slightly smaller Jupiter. The rings will be a memory, a footnote in astronomical records. We are lucky to be alive right now, lucky to exist in the narrow slice of cosmic time when Saturn wears its crown. But the rings are not the only extraordinary feature on this planet. At Saturn's North Pole, something else defies explanation. A geometric shape that has no business existing in a churning atmosphere of hydrogen and helium. A shape that has been spinning for decades, possibly centuries, and that stretches higher into the atmosphere than anyone predicted. A hexagon, perfect, persistent, and profoundly strange. Chapter 3: The Hexagon, Nature's Forbidden Shape. In 1981, NASA's Voyager spacecraft flew past Saturn and captured images of the planet's North Pole. Buried in that data, unnoticed for years, was something that should not exist: a hexagon. Not a vague, hexagonal-looking pattern, not an approximation, a precise, six-sided polygon embedded in Saturn's atmosphere, centered almost perfectly on the North Pole, with each of its 6 sides stretching roughly 9,000 miles long. That is longer than the diameter of Earth. The entire hexagon spans roughly 18,000 miles corner to corner. You could fit 2 Earths inside it and still have room. David Godfrey discovered it in 1987 by piecing together images from the Voyager flybys. At first, many scientists were skeptical. A hexagon in a fluid atmosphere? Atmospheres are chaotic. They swirl, they eddy, they dissolve structure. Straight lines and sharp angles are the language of crystals and geometry, not turbulent gas. How could a planetary atmosphere, composed entirely of hydrogen and helium in constant motion, sustain a rigid geometric shape? When the Cassini spacecraft arrived at Saturn in 2004, the North Pole was shrouded in winter darkness. Cassini could not photograph the hexagon in visible light, but its visual and infrared mapping spectrometer, an instrument that could see in wavelengths beyond human vision, pierced the darkness. The hexagon was still there. 25 years after Voyager first glimpsed it, the structure had barely changed. Same shape, same position, same rotational period. As Saturn's northern hemisphere crept towards spring and sunlight returned to the pole, Cassini's visible light cameras captured the hexagon in extraordinary detail. The images were stunning. A vast jet stream of atmospheric gases moving at roughly 300 miles per hour locked into a hexagonal path, rotating with a period of 10 hours 39 minutes and 24 seconds. That is almost exactly Saturn's internal rotation period, the spin rate of the planet's deep interior. The hexagon does not drift. It does not wander. It is anchored to the planet itself, spinning with it like a feature carved into the atmosphere's bedrock. At the center of the hexagon sits a cyclone, a massive polar vortex roughly 50 times the size of a typical hurricane on Earth, with an eye so distinct and well-defined that it resembles a terrestrial hurricane photographed from space. Winds within this polar cyclone exceed 300 miles per hour. And unlike hurricanes on Earth, which form over warm oceans and dissipate when they make landfall or move over cold water, this storm has no ocean to feed it and no land to stop it. It simply spins, year after year, decade after decade, possibly for centuries. Within the hexagon, smaller vortices dot the landscape. Some spin clockwise, some spin counterclockwise. The largest is roughly 2,200 miles across, about twice the size of the biggest hurricane ever recorded on Earth. These vortices are swept along the hexagonal jet stream like boats caught in a current, racing around the pole in an endless circuit. Between 2012 and 2016, Cassini watched the hexagon change color. When the spacecraft first captured it in visible light, the hexagon appeared a deep, striking blue. By the end of Cassini's mission, it had shifted to gold. Scientists believe this color change is linked to Saturn's seasons. As the North Pole tilted toward the sun and summer approached, ultraviolet radiation began producing photochemical haze, smog particles that accumulated in the atmosphere and gave the hexagon its warm, golden hue. The center of the vortex, however, remained blue, suggesting different chemical processes or airflow patterns at the very core of the storm. But perhaps the most surprising discovery came not from the clouds below, but from the atmosphere above. In 2018, Lee Fletcher of the University of Leicester published a study in Nature Communications revealing that the hexagonal shape extends far higher into Saturn's atmosphere than anyone thought possible. Using data from Cassini's composite infrared spectrometer, Fletcher and his team found that as Saturn's northern hemisphere warmed into summer, a stratospheric vortex formed high above the cloud-level hexagon. And this upper atmosphere vortex was also hexagonal. The hexagon, it turned out, was not just a shallow surface feature, it was a towering column of structured atmosphere, spanning more than 300 kilometers in height from the troposphere into the stratosphere. A Rossby wave, a type of large-scale atmospheric wave driven by the rotation of the planet, appeared to be punching upward through layers of atmosphere, imposing its geometric discipline on air masses hundreds of miles above the cloud deck. Nothing like this had ever been observed on any other planet. Jupiter, Saturn's larger cousin, has a completely different polar structure. The Juno spacecraft revealed that Jupiter's North Pole hosts not one but 9 cyclones, 8 arranged in a ring around a central ninth, like a pattern of swirling cinnamon rolls. No hexagon, no geometric symmetry, just a cluster of storms jostling for position. Why the difference? In 2026, researchers at the Massachusetts Institute of Technology published a study offering a potential explanation. Ji Shi and Wanying Kang found that the key variable may be the size and wind speed of the central polar vortex. On Jupiter, the polar cyclone is relatively small and fast, allowing multiple secondary vortices to form around it in a polygonal arrangement. On Saturn, the polar cyclone is larger and its winds slower, which prevents the formation of multiple secondary vortices, but instead supports a single meandering jet stream that locks into a hexagonal wave pattern through a process called barotropic instability. The Oxford experiment shed further light. Physicists Ana Claudia Barbosa Aguiar and Peter Redd at the University of Oxford placed liquid in a circular tank and rotated the center and the edges at different speeds. The difference in rotation created a shear zone between the two fluid bodies. As the speed difference increased, the boundary between the two fluids stopped being circular and began forming polygons, triangles, squares, pentagons, and yes, hexagons. The number of sides depended on the ratio of rotation speeds. When the ratio matched the conditions estimated for Saturn's north polar jet stream relative to the surrounding atmosphere, the result was a hexagon. But there is a catch. The laboratory hexagons were unstable. They required specific, carefully controlled boundary conditions to persist. Change the speed slightly and the hexagon dissolved into a pentagon or a heptagon. In the laboratory, maintaining a hexagon for more than a few minutes required constant attention. Saturn's hexagon has maintained its shape for at least 45 years, likely much longer, possibly centuries. How does a turbulent, convective atmosphere maintain the precise conditions needed to sustain a geometric wave pattern for that long? A 2020 study published in the Proceedings of the National Academy of Sciences by researchers at Harvard University proposed that the answer lies deep, very deep. Saturn's hexagonal jet stream is not a shallow weather phenomenon. It is driven by convection currents rising from thousands of kilometers below the cloud tops, powered by the planet's internal heat. These deep convective forces create and maintain the zonal jets, the alternating bands of east and west wind that encircle Saturn at different latitudes. The hexagonal jet at 78 degrees north latitude is one of these deep jets, locked into its geometric pattern by the interaction between its own eastward flow and the surrounding atmospheric vortices that act as stabilizing anchors. In other words, the hexagon may not be a surface oddity. It may be a window into the deep interior of Saturn itself, a visible signature of convective processes happening tens of thousands of miles below the clouds. The atmosphere is not just displaying weather, it is displaying structure, the internal machinery of the planet, grinding away beneath layers of compressed gas, is stamping its signature onto the visible cloud deck, in the form of a perfect geometric pattern. There is something almost sacred about it. Hexagons appear throughout nature, the cells of a honeycomb, the basalt columns of the Giant's Causeway, the crystal structure of snowflakes, the compound eyes of insects. In each case, the hexagon emerges because it is the most efficient way to tile a surface with equal-sized cells, the shape that encloses the maximum area with the minimum perimeter. It is nature's preferred geometry when efficiency and stability are the goals. And here, at the North Pole of a gas giant 900 million miles from Earth, the same geometry appears, not in crystal, not in biology, in wind. Saturn's South Pole, by contrast, has no hexagon, just a massive cyclone, swirling without geometric structure. The asymmetry between the two poles remains an active area of research, hinting at fundamental differences in the atmospheric dynamics or the deep convective patterns beneath each hemisphere. The hexagon asks a question that science has not fully answered. Can we ever truly understand a planet whose atmosphere encodes mathematics into weather? A planet where the invisible forces shaping wind patterns create geometry that mirrors the most efficient structures in the biological world. If the hexagon is unsettling in its perfection, what happens next on Saturn is unsettling in its violence. Because roughly once every 30 Earth years, the planet's atmosphere tears itself apart. A storm erupts. Not a small storm, not a regional disturbance. A superstorm so vast it wraps around the entire planet. A tempest so electrically charged it produces lightning 10 times more powerful than anything on Earth. Saturn calls these events the Great White Spots, and the next one could happen any year now. Chapter 4. The Great White Spot. When Saturn goes to war with itself. Saturn, most of the time, looks calm, banded, orderly, pale gold and butterscotch stripes wrapping the planet in horizontal layers, each band a jet stream of gas moving at its own speed and latitude. Compared to Jupiter with its raging great red spot and turbulent cloud formations, Saturn appears almost serene. That serenity is a lie. Roughly once every 20 to 30 years, something detonates inside Saturn's atmosphere. A massive upwelling of warm, moist air punches through the upper cloud deck and erupts into a visible white spot, brilliant against the planet's muted tones. Within days, the spot grows. Within weeks, it begins to stretch. Within months, it has encircled the entire planet, a belt of churning white cloud and violent electrical discharge that can persist for the better part of a year. These are the Great White Spots, the most powerful storms in the solar system, and they are unique to Saturn. 6 of these superstorms have been observed since 1876. The first was spotted by Asaph Hall, the American astronomer better known for discovering the moons of Mars. He used the bright spot to calculate Saturn's rotation period. In 1933, Will Hay, a British comic actor and amateur astronomer, observed another. The 1960 event appeared at high northern latitudes. The 1990 storm erupted near the equator and was tracked by both ground-based telescopes and the Hubble Space Telescope. But the most thoroughly studied Great White Spot was the one that erupted in December of 2010. This time, the Cassini spacecraft was in orbit around Saturn, equipped with instruments that could observe the storm from every angle and in every wavelength. What Cassini recorded was extraordinary. The storm began as a small white cloud, roughly 800 miles across, at about 32 degrees north latitude. Within 3 weeks, it had grown to 10,000 miles from north to south and 17,000 miles from east to west. If an equivalent storm formed on Earth, it would blanket most of North America from top to bottom. But this storm did not stop growing. As Saturn's powerful zonal winds sheared the storm cloud, a tail began streaming eastward. This tail lengthened at a remarkable pace, propelled by jet streams moving at different speeds at different latitudes. 12 weeks after the storm began, the tail had wrapped completely around the planet. The head of the storm, still churning and actively convecting, eventually collided with its own tail. When the head met the tail, the storm's convective activity weakened and ceased within about 50 days, but the atmospheric disturbance persisted for years. Cassini's instruments revealed that the storm was not merely a surface phenomenon. It was a three-dimensional monster. The convective towers within the storm, columns of rising warm air, extended 10 to 20 times higher than a typical thunderstorm on Earth. Fresh water ice, ammonia ice, and ammonium hydrosulfide particles were carried from deep in Saturn's atmosphere to the visible cloud tops, giving the storm its characteristic white appearance. The spectral analysis performed by Cassini's visual and infrared mapping spectrometer found that the storm's cloud particles were roughly 55% ammonia ice, 22% water ice, and 23% ammonium hydrosulfide. This was significant because it marked the first direct detection of water ice in a Saturnian storm, confirming that the upwelling was drawing material from deep atmospheric layers where temperatures are low enough for water to condense. And then there was the lightning. Saturn's lightning is unlike anything on Earth. Cassini detected electrostatic discharges from the storm using its radio and plasma wave science instrument. At the peak of the storm, lightning flashed more than 10 times per second. Each flash released energy roughly 10,000 times greater than a typical lightning bolt on Earth. The total energy output of the storm was estimated at 10 to the 17th watts, a number so large it is difficult to grasp. For context, it is comparable to a significant fraction of all the energy Saturn radiates into space. This single storm was pumping out power equivalent to what the Earth receives from the Sun in an entire year. The sound of Saturn's lightning, translated into radio frequencies detectable by Cassini's instruments, was a crackling, hissing roar. Scientists nicknamed these discharges Saturn electrostatic discharges, or SEDs. During previous smaller storms in Saturn's so-called storm alley, a latitude band in the southern hemisphere where smaller convective events had been erupting regularly since 2004, SEDs were detectable but modest. The 2010 Great White Spot produced SEDs continuously for months, a non-stop electrical barrage without parallel in the observed solar system. But why? Why does Saturn produce these colossal storms so infrequently? Why not constantly, like Jupiter's persistent Great Red Spot? The answer, proposed by Cheng Li and Andrew Ingersoll of the California Institute of Technology and published in the journal Nature Geoscience in 2015, lies in the behavior of water vapor in Saturn's hydrogen-helium atmosphere. Saturn's atmosphere is layered. Deep inside, where temperatures and pressures are high, water exists as vapor mixed with the dominant hydrogen and helium. As you move upward toward the cloud tops, temperatures drop. On Earth, cooling air allows water vapor to condense, forming clouds and rain. On Saturn, the process is similar but complicated by a critical detail. Water vapor is heavier than the surrounding hydrogen and helium atmosphere. When the upper atmosphere cools, water vapor begins to rain out. As it does, the upper layers lose their heaviest component. They become less dense, lighter. This creates a situation where the upper atmosphere is actually less dense than the layers below, a condition called convective inhibition. The lighter upper layer acts like a lid, preventing the warmer, moister air below from rising. Convection is suppressed. The atmosphere stabilizes. Storms cannot form. But the cooling continues. Over decades, the upper atmosphere keeps radiating heat into space. It gets colder and colder. Eventually, the cooling overcomes the density inversion. The upper layer becomes dense enough, cold enough, that the lid breaks. Warm, moist air from below erupts upward in a massive convective burst. Water condenses. Ice forms. Lightning crackles. The Great White Spot is born. The process then resets. The eruption releases so much energy and moisture that it re-establishes the density inversion. The lid closes again, and Saturn waits another 20 to 30 years, cooling slowly, building pressure until the next eruption. Lee and Ingersoll tested this theory against observations of the 2010 storm and found strong agreement. They also proposed that Jupiter lacks great white spots because Jupiter's atmosphere contains less water vapor than Saturn's. Without enough water to create a strong density inversion, Jupiter's convection is never fully suppressed, which is why Jupiter has continuous storm activity rather than periodic explosions. Saturn bottles up its energy and releases it all at once. Jupiter leaks it steadily. The 2010 storm did something else remarkable. It disrupted Saturn's stratosphere. As the convective towers pumped material upward, two warm air masses formed in the stratosphere, high above the storm, like blisters of heated gas. Cassini's composite infrared spectrometer tracked these features as they drifted around the planet. In early 2012, the two warm masses merged. The resulting temperature spike was extraordinary. Temperatures in the merged beacon rose by over 80 degrees Kelvin, creating the warmest spot ever recorded in Saturn's stratosphere. Along with the heat came a chemical signature. Ethylene, a simple hydrocarbon not typically abundant in Saturn's stratosphere, was detected in unusually high concentrations. The merged beacon was not just warm. It was chemically altered, a stratospheric eruption triggered by a tropospheric storm, demonstrating that Saturn's weather operates as a connected system spanning hundreds of kilometers in depth. The pattern of great white spots suggests they occur roughly once per Saturnian year, or about every 29.5 Earth years. They tend to appear when Saturn's northern hemisphere is most tilted toward the Sun, suggesting a seasonal trigger. Although the exact mechanism linking solar illumination to the deep atmospheric instability remains uncertain, the last great white spot erupted in 2010. The next one, by historical pattern, could appear sometime in the late 2030s. But the 2010 event was unusual. It erupted earlier than expected and at a latitude that did not match the typical progression. In 2018, ground-based telescopes detected a series of 4 mid-sized storms near Saturn's North Pole, each several thousand kilometers across, that some scientists interpreted as a failed great white spot, a partial eruption that lacked enough energy to develop into a full-scale planetary event. Saturn, it seems, tried to produce a superstorm and could not quite manage it. The 2010 event may have drained so much energy from the atmosphere that the 2018 disturbance fizzled. The planet was still recovering, still recharging. This is a world that stores energy for decades, then unleashes it in a single catastrophic event. A world where silence does not mean peace. It means pressure is building. It means the next eruption is not a question of if, but when. And while these storms rage across Saturn's cloud tops, something equally dramatic is happening nearly 1 billion miles away on a moon, so eerily similar to Earth that scientists call it a twin. Not a twin in temperature, not a twin in hospitality, a twin in process, in weather, in landscape, in the fundamental machinery of a world with an atmosphere, with rain, with rivers, with lakes and seas. Except on this moon, the rain is not water, the rivers are not water, the seas are not water. They are liquid methane and ethane, and the surface temperature is -179 degrees Celsius. Welcome to Titan. Chapter 5. Titan, Earth's evil twin. Before Cassini arrived at Saturn in 2004, Titan was a mystery wrapped in orange haze. We knew it was large, roughly 5,100 kilometers in diameter, bigger than the planet Mercury. We knew it had a dense atmosphere, the only moon in the solar system with a substantial one, composed primarily of nitrogen, with a surface pressure about 1.5 times that of Earth. We knew methane was present in that atmosphere in significant quantities, and we knew almost nothing else. because the thick photochemical smog that blankets Titan is opaque to visible light. No camera, no telescope, no spacecraft flying past at speed had ever seen the surface clearly. Titan was a locked box. Cassini brought the key. The Cassini orbiter carried instruments that could see through the haze. Radar, which sent radio pulses down through the atmosphere and read the echoes bouncing back from the surface. Infrared cameras, which could penetrate the smog at specific wavelengths. And riding along with Cassini was Huygens, a probe built by the European Space Agency designed for one purpose: to drop through Titan's atmosphere, measure everything on the way down, and land on the surface. On January 14, 2005, Huygens separated from Cassini and began its descent. It fell for 2.5 hours through orange sky, buffeted by winds, slowed by parachutes, its instruments sampling the atmosphere at every altitude. The data streamed back to Cassini overhead, which relayed it to Earth. What Huygens found was astonishing. The atmosphere was layered, with different temperatures, pressures, and wind speeds at different altitudes. Methane was present not just as a trace gas, but as a major atmospheric constituent, behaving on Titan the way water behaves on Earth. It evaporated from the surface, it rose into the atmosphere, it condensed into clouds, it fell as rain, and it collected on the ground in liquid form. Huygens photographed the surface as it descended. The images showed a landscape eerily reminiscent of a desert coastline on Earth. Dark, flat areas bordered by lighter, elevated terrain. Drainage channels carved into the surface, branching like river systems, flowing from highlands down toward the dark lowlands. Rounded pebbles, smoothed by the flow of liquid, scattered across the landing site. When Huygens touched down, its instruments detected that the ground was damp, not wet with water, wet with hydrocarbons. This was the first landing in the outer solar system, the first time a human-made instrument had rested on the surface of a world in the Saturn system. And what it found was a world that, despite being nearly minus 180 degrees Celsius, had an active hydrological cycle. Not a water cycle, a methane cycle, but the processes were identical: evaporation, condensation, precipitation, surface flow, collection into standing bodies of liquid. The same fundamental cycle that drives weather and shapes landscapes on Earth, operating on an alien world with alien chemistry. Over the following 13 years, Cassini completed more than 100 targeted flybys of Titan, building a comprehensive picture of the Moon's surface and atmosphere. The radar revealed a world of extraordinary diversity. At the equator, vast fields of sand dunes stretched for hundreds of miles, their dark organic material sculpted by wind into parallel ridges resembling the sand seas of the Sahara or the Namib Desert. These dunes are not made of silicate sand. They are made of complex organic molecules, tholins, produced by photochemistry in Titan's upper atmosphere and settling to the surface like a fine, dark snow. Near the poles, the landscape transforms. Cassini's radar discovered something that had been theorized for decades but never confirmed: lakes and seas of liquid methane and ethane. Dozens of them in the northern hemisphere, only one in the south. The largest, Kraken Mare, covers roughly 400,000 square kilometers, larger than the Caspian Sea on Earth. Ligeia Mare, the second largest, was probed by Cassini's radar and found to have depths exceeding 160 meters. The radar also detected the bottom of the sea and found it covered in a sludge of organic compounds. Heavy molecules that fall from the sky, dissolve partially in the liquid methane, and settle to the seabed. The smaller lakes are perched on hilltops, surprisingly deep, and filled primarily with methane rather than the expected methane-ethane mixture. Their existence on elevated terrain suggests they are fed by subsurface methane reservoirs, a hydrocarbon aquifer that saturates the ground and surfaces at certain points, much like springs and seeps on Earth. Titan has rain. Modeled by climate scientists, the rain on Titan falls differently than on Earth. Earth's atmosphere can hold roughly 2 centimeters of precipitable water. Titan's atmosphere can hold the equivalent of 10 meters of methane before rain forms. This means Titan's weather alternates between long periods of drought, possibly lasting decades or centuries, and enormous downpours. When rain comes to Titan, it comes in torrents. Meters of liquid methane falling from the sky, carving flash floods through the organic sand dunes and filling dry lake beds in a single event. Cassini observed equatorial rainstorms only once during its entire 13-year mission in 2009. Further evidence that Titan's precipitation is rare but intense. The hydrocarbon wealth on Titan is staggering. Ralph Lorenz of the Johns Hopkins University Applied Physics Laboratory calculated that Titan's surface contains hundreds of times more liquid hydrocarbons than all the known oil and natural gas reserves on Earth. Dozens of individual lakes hold more energy in the form of methane and ethane than the entire proven natural gas reserve of our planet. Titan is, quite literally, a world swimming in fuel. But the most provocative question about Titan is not about its geology or its weather. It is about life. Could something live there? On Earth, life requires liquid water. Every organism we know of, from the simplest bacterium to the largest whale, uses water as a solvent, the medium in which biochemical reactions occur. Titan has no liquid water on its surface. The temperature is far too low. Water exists on Titan only as rock-hard ice, a geological material rather than a biological one. But Titan has liquid. Methane and ethane flow across its surface and fill its seas. Could life evolve to use a hydrocarbon solvent instead of water? In 2005, astrobiologists Christopher McKay and Heather Smith proposed a thought experiment. What if organisms on Titan consumed hydrogen from the atmosphere and reacted it with acetylene instead of glucose, producing methane as a waste product instead of carbon dioxide? Such organisms would be methanogens, using the same basic metabolic strategy as certain archaea on Earth, but adapted to a completely different chemical environment. McKay and Smith predicted that if such life existed in significant quantities, it would measurably deplete hydrogen and acetylene near Titan's surface. In 2010, Darrell Strobel of Johns Hopkins University analyzed Cassini data and reported anomalies consistent with these predictions. Hydrogen appeared to be flowing downward from the upper atmosphere and disappearing near the surface at a rate that chemical models could not easily explain. Acetylene, which should be abundant on Titan's surface as a product of atmospheric chemistry, was present in much lower concentrations than expected. This is not proof of life. There are non-biological explanations. An unknown catalytic surface process could be consuming the hydrogen. The acetylene might be trapped in subsurface reservoirs or chemically bound to surface materials. But the data was provocative. It fit the profile of a biosphere too neatly to be ignored. In 2015, researchers at Cornell University proposed a theoretical cell membrane that could function in liquid methane. They called it an azotosome, a membrane made of nitrogen containing organic molecules called acrylonitrile, which Cassini and later the Atacama Large Millimeter Array confirmed is present in Titan's atmosphere in substantial quantities. Unlike the phospholipid membranes of Earth life, which require water, azotosomes could self-assemble and maintain structural integrity in liquid methane at Titan's surface temperatures. In 2025, astrobiologists Christian Mayer and Connor Nixon proposed a mechanism by which the interaction between small mist droplets and the surface of methane lakes could overcome barriers to the formation of these exotic membranes, potentially providing a pathway from simple chemistry to organized structures. Whether life exists on Titan remains one of the great open questions in science. The Dragonfly mission, A NASA rotorcraft lander scheduled to arrive at Titan in the 2030s is designed to explore the Moon's surface in unprecedented detail, sampling organic chemistry and searching for biosignatures. Dragonfly will fly from site to site across Titan's surface, covering more ground than any planetary rover in history, powered by the radioactive decay of plutonium in the cold, dim environment where solar panels are useless. But Titan is not the only moon of Saturn with astrobiological significance. In fact, it may not even be the most promising. That distinction may belong to a moon so small it would fit inside the borders of the United Kingdom. A world of brilliant white ice that nobody expected to be interesting at all. And then Cassini saw what was erupting from its south pole. Chapter 6. Enceladus, the moon that bleeds into space. Enceladus is tiny, roughly 300 miles across. You could drive its diameter in a few hours on a highway. It is one of the smallest objects in the solar system, known to be geologically active. And for most of the history of planetary science, nobody paid it much attention. It was just another icy moon in Saturn's crowded court, white, cold, apparently dead. That changed in 2005, when Cassini arrived at Saturn and began its survey of the planet's moons. It flew past Enceladus and saw something that rewrote the textbook. The spacecraft's magnetometer detected a disturbance in Saturn's magnetic field near the moon, as if something was pushing against it, something like an atmosphere. But Enceladus was far too small and too cold to hold an atmosphere by conventional physics. Its gravity was negligible. Any gas released from its surface should have escaped into space almost immediately. Cassini looked closer. Its cameras revealed 4 enormous parallel fractures near the south pole of Enceladus, each roughly 135 kilometers long, cutting deep into the ice. Scientists named them the tiger stripes, and from these fractures, towering plumes of material were erupting into space. Jets of water vapor, ice crystals, and organic molecules shooting hundreds of kilometers above the surface at roughly 800 miles per hour, high enough and fast enough to escape the moon's feeble gravity entirely. This was not volcanism in the traditional sense. There was no molten rock, no lava. This was cryovolcanism, cold volcanism. Liquid water from beneath the ice shell was being forced through cracks and vented into the vacuum of space, where it instantly froze into glittering ice particles. The plumes were so prolific that they were feeding Saturn's entire E-ring, the diffuse outer ring of tiny ice particles that had puzzled astronomers for decades. Enceladus was not just geologically active, it was actively building one of Saturn's rings. Over the next 12 years, Cassini made over 20 close flybys of Enceladus, each one revealing more about this improbable little world. The discoveries came in waves, each more startling than the last. First, the ocean. Gravity measurements taken during close passes revealed that Enceladus was slightly deformed, its mass distribution uneven in a way that suggested a large body of liquid water beneath the ice. By 2014, analysis of the moon's libration, a slight wobble in its rotation caused by Saturn's gravitational tug, confirmed what many suspected. The ice shell was not resting on a solid interior, it was floating on a global ocean, a sea of liquid water completely encircling the rocky core of the moon, hidden beneath roughly 20 to 25 kilometers of ice. Near the South Pole, where the tiger stripes cut through, the ice may be as thin as a few kilometers. Second, the salt. Cassini's cosmic dust analyzer sampled ice grains from the plumes and from Saturn's E-ring. The grains contained sodium chloride, table salt, in concentrations similar to Earth's oceans. Salt water. The ocean of Enceladus is not pure water. It is a salty, mineral-rich solution, the kind of liquid that forms when water interacts with rock over long periods. This was powerful evidence that the ocean was in direct contact with the moon's rocky core, leaching minerals the way seawater on Earth interacts with the ocean floor. Third, The silica. Among the ice grains Cassini collected were nanoscale particles of silica, tiny grains of silicon dioxide between 2 and 8 nanometers in size. On Earth, silica nanoparticles of this precise size form in only one way. Hot water, heated to at least 90 degrees Celsius, rises through rock, dissolving minerals. When this hot, mineral-laden water meets cooler water above, the dissolved silica precipitates out as nanoparticles. This is exactly what happens at hydrothermal vents on Earth's ocean floor. The implication was unmistakable. Enceladus has hydrothermal vents. At the bottom of its ocean, hot water is emerging from the rocky core, carrying dissolved minerals into the cooler sea above. The same type of geological process that powers the ecosystems around Earth's mid-ocean ridges and black smokers is operating inside a moon 300 miles wide in the outer solar system. Fourth, the hydrogen. On October 28, 2015, Cassini made its deepest dive through the Enceladus plume, passing just 49 kilometers above the surface. The ion and neutral mass spectrometer, sampling the gas directly, detected significant quantities of molecular hydrogen. Hunter Waite of the Southwest Research Institute led the analysis, published in the journal Science in April 2017. The team concluded that the most plausible source of this hydrogen was ongoing hydrothermal reactions between water and rock containing reduced minerals, a process called serpentinization. Serpentinization is one of the most important geochemical processes on Earth. When water reacts with iron and magnesium-rich minerals in rock, it produces serpentine minerals and releases hydrogen gas as a byproduct. This hydrogen is not just a chemical curiosity, it is an energy source. On Earth, microorganisms called methanogens use hydrogen to reduce carbon dioxide into methane, extracting energy from a purely chemical reaction that requires no sunlight whatsoever. These organisms form the base of entire ecosystems in the deep ocean, ecosystems that thrive in complete darkness, powered not by the sun but by the chemistry of rock and water. The discovery of hydrogen in the plume meant that Enceladus possesses a chemical energy source capable of supporting life. Not theoretically, not in some distant future scenario, right now. The thermodynamic disequilibrium between the hydrogen being produced and the carbon dioxide dissolved in the ocean creates a potential energy gradient that biology could exploit. The ingredients are there: liquid water, chemical energy, organic molecules, mineral nutrients, time. How much time? Estimates vary, but the hydrothermal activity on Enceladus appears to have been ongoing for at least 40 million years, possibly more than 100 million years. On Earth, the earliest evidence of life appears roughly 500 million years after the planet's formation. If Enceladus has had liquid water and chemical energy for even 40 million years, there has been more than enough time for life to emerge. If the processes that lead from chemistry to biology are as universal as many scientists suspect. Fifth, the organics. Cassini detected organic compounds in the plume, both simple molecules like methane and carbon dioxide, and more complex species. In 2018, Frank Postberg of the University of Heidelberg and his colleagues published a study in Nature announcing the detection of large, complex organic molecules in Enceladus's plume, with molecular weights above 200 atomic mass units. These were not simple methane or ethanol. These were fragments of much larger molecules, possibly including nitrogen and oxygen-bearing compounds, the kinds of molecules associated with prebiotic chemistry and the building blocks of life. In 2023, the identification of phosphates in the plume grains was announced, meaning that 5 of the 6 elements essential for life as we know it, carbon, hydrogen, nitrogen, oxygen, and phosphorus, have now been confirmed in material originating from Enceladus's ocean. Only sulfur remains undetected, and many scientists consider its presence likely given the geochemistry involved. In 2025, A reanalysis of Cassini data from its highest-speed flyby of Enceladus revealed an even richer chemistry. Aliphatic compounds, cyclic esters, ethers, and tentatively, nitrogen and oxygen-bearing molecules were identified in freshly ejected ice grains. The ocean of Enceladus is not a sterile pool of salt water. It is a chemically rich, dynamic environment undergoing the kinds of reactions that, on Earth, are intimately connected to biology. Morgan Cable of NASA's Jet Propulsion Laboratory put it simply: let us say you have all the ingredients for life there, but no life yet. Wait about 10 million years and you should have life. And the liquid water, the heat, and the inferred hydrothermal activity on Enceladus have been going on for 40 million years or more, maybe more than 100 million years. If you compare that against the 10 million years, there is plenty of time for life to have emerged. It seems like all the ingredients are there. The question is life there? We do not know. Cassini was not equipped to detect life. It was launched in 1997, years before anyone knew Enceladus had a plume, or an ocean, or hydrothermal vents. Its instruments were designed for a different era and a different set of questions. Detecting biosignatures, proteins, amino acid patterns, lipid membranes, metabolic byproducts requires instruments that did not exist when Cassini was built, is less than #0. 5 hash is greater than. The next step is to go back. To fly through the plume again with modern instruments designed specifically to answer the question. To go fishing, as Chris Glein of the Southwest Research Institute phrased it, but in a very methodical manner. NASA has identified Enceladus as a high-priority target for future exploration, and mission concepts are under development. The plume is an extraordinary gift. It is literally spraying the contents of the ocean into space. You do not need to drill through miles of ice to sample the water. You just need to fly through the spray. Enceladus may be the best place in the solar system to search for extraterrestrial life. Better than Mars, where liquid water existed billions of years ago but may be gone now. Better than Europa, Jupiter's ocean moon, where we suspect an ocean exists but have no plume to sample easily. Enceladus is offering its ocean to us, shooting it into space, begging to be studied. And yet, as remarkable as Enceladus is, it is only one of Saturn's 146 known moons. The system is vast, and deep inside the planet itself, beneath the clouds and the storms and the hexagon, lies a realm so extreme that it challenges the very definition of matter. A place where hydrogen becomes metal, where helium falls as rain, and where carbon may be crushed into diamonds that drift downward through the darkness, like gemstones sinking in oil. Saturn's interior is a world unto itself, and it is far stranger than anything on the surface. Chapter 7: Saturn's Hidden Interior, the planet that should not exist. If you could fall into Saturn, this is what would happen. You would enter the atmosphere at the cloud tops, where the temperature is roughly -178 degrees Celsius, and the pressure is about 1 bar, the same as sea level on Earth. The sky would be a pale gold haze. Ammonia ice crystals would drift around you. Bands of cloud, moving at different speeds at different latitudes, would stretch to every horizon. You would fall, and as you fell, everything would change. Within a few hundred kilometers, the temperature would rise, the pressure would climb, the ammonia clouds would give way to ammonium hydrosulfide, then to water ice clouds deeper still. The sky would darken as the photochemical haze thinned and sunlight could no longer penetrate. Eventually, there would be no light at all, just heat, pressure, and the increasing density of hydrogen gas around you. At roughly 1,000 kilometers below the cloud tops, the temperature would reach about 1,000 Kelvin and the pressure roughly 1,000 bars, 1,000 times Earth's surface pressure. At these conditions, hydrogen is no longer a gas, it is a liquid. You would not crash into an ocean. There would be no surface. The gas would simply thicken, gradually, imperceptibly, until you were swimming in liquid hydrogen without ever having crossed a boundary. On Saturn, the transition from gas to liquid is continuous. There is no surface, no shoreline, no edge, just a gradient, a smooth increase in density that turns atmosphere into ocean without announcement. Deeper still, at roughly half the distance from the cloud tops to the center, the pressure would reach approximately 2 million bars, 2 megabars, and the temperature about 6,000 Kelvin, roughly the temperature of the surface of the Sunday. At these conditions, something extraordinary happens. Hydrogen changes its nature. In the outer layers, hydrogen exists as molecules, two hydrogen atoms bonded together, vibrating, tumbling, acting like the everyday gas we know. But at 2 megabars, the pressure is so extreme that the molecular bonds break. Electrons are stripped from their atoms and become free to move. The hydrogen becomes metallic. It conducts electricity. It reflects light, although there is no light to reflect down here. It behaves like a liquid metal, resembling molten lithium or sodium, not the light, invisible gas you breathe on Earth. This transition from molecular to metallic hydrogen is one of the most important phase changes in planetary science. It is the reason Saturn has a magnetic field. The metallic hydrogen layer, conducting electricity while being stirred by convection currents, acts as a dynamo. Slow circulating currents in this liquid metal generate a magnetic field that extends far beyond the planet, shaping the paths of charged particles, influencing the orbits of ring particles, and creating the invisible architecture of Saturn's magnetosphere. Saturn's magnetic field is peculiar. On Earth, Jupiter, and most other magnetic planets, the magnetic axis is tilted relative to the rotation axis. Earth's magnetic poles are offset from the geographic poles by roughly 11 degrees. Jupiter's offset is about 10 degrees. Saturn's offset is essentially 0. The magnetic field is almost perfectly aligned with the rotation axis, exhibiting a near-perfect axial symmetry that is unique in the solar system. This symmetry puzzled scientists for decades. Dynamo theory predicts that a perfectly symmetric magnetic field should not be stable. It should wobble, tilt, and drift. The fact that Saturn's field remains so perfectly aligned suggests something is smoothing it out. The leading explanation, supported by Cassini gravity data and modeling by Sabine Stanley at Johns Hopkins University, is that a thick layer of helium rain between the metallic hydrogen dynamo region and the outer molecular hydrogen envelope acts as a filter. This helium-insoluble layer absorbs asymmetries in the magnetic field before they can reach the surface, presenting a deceptively smooth, symmetric face to the outside universe. Helium rain. The concept sounds almost poetic, but it describes a brutally physical process. Deep inside Saturn, the pressure and temperature conditions are such that helium, which normally mixes freely with hydrogen, becomes insoluble. The helium separates from the hydrogen like oil separating from water. It condenses into droplets, and those droplets, denser than the surrounding metallic hydrogen, fall. They rain downward through the interior, settling toward the center of the planet. This process was first proposed theoretically in the 1970s by David Stevenson, then at the California Institute of Technology. It was invoked to solve a specific problem. Saturn is too bright. It radiates roughly 2.5 times more energy into space than it receives from the Sunday. Jupiter does this too, but Jupiter's excess heat can be explained by the slow cooling of a planet that was very hot when it formed. Saturn, being smaller, should have cooled faster and should no longer be radiating excess heat at this rate. Something is providing additional energy. Helium rain provides it. As helium droplets fall, they convert gravitational potential energy into kinetic energy, which is ultimately dissipated as heat. The settling of helium through the interior acts like a slow, continuous energy source, keeping Saturn warmer than it should be. The process also explains why Saturn's atmosphere appears to be depleted in helium compared to the Sun and compared to Jupiter. The helium has not vanished, it has sunk. It is concentrated in the deep interior, hidden from direct observation. In 2016, Gilbert Collins and his colleagues at Lawrence Livermore National Laboratory provided the first experimental evidence for helium rain at conditions relevant to Saturn. Using the Omega laser at the University of Rochester, they compressed a mixture of hydrogen and helium between diamond anvils and then blasted it with shock waves. At specific temperature and pressure thresholds, the helium separated from the hydrogen exactly as predicted. The experimental conditions matched those expected in Saturn's interior. Remarkably, the experiments also suggested that helium rain might occur on Jupiter as well, where the conditions were previously thought to be too hot. And then there are the diamonds. Saturn's atmosphere contains methane, not in large quantities, but enough. Methane is a molecule of one carbon atom bonded to 4 hydrogen atoms. Deep in the atmosphere, where lightning strikes and temperatures soar, methane molecules can be broken apart. The carbon is freed. And as this liberated carbon sinks deeper into the planet, encountering ever greater pressures and temperatures, it undergoes a series of transformations. First, the carbon atoms link together to form soot. Then, as pressure climbs past the threshold, the soot is compressed into graphite. And then, deeper still, the graphite is crushed into diamond. Diamond rain, crystals of pure carbon, formed in the incandescent depths of a gas giant, falling through layers of liquid metallic hydrogen toward a core that may not even be solid. Laboratory experiments have confirmed that this process is physically plausible. In 2017, researchers at the SLAC National Accelerator Laboratory used high-powered lasers to recreate the conditions found deep inside ice giant planets and demonstrated that carbon does indeed form diamond structures under extreme pressure. Similar conditions exist within Saturn and Jupiter, where the diamonds would be larger and the process more vigorous. The diamonds would not sparkle. There is no light in Saturn's interior. They would form in darkness, fall in darkness, and accumulate if they survive the heat and pressure. Somewhere in the transition zone between the metallic hydrogen layer and the fuzzy core, some models suggest the diamonds might eventually melt in the extreme temperatures near the core, forming a layer of liquid carbon, a sea of diamond, surrounding the center of the planet. Other models suggest they dissolve into the metallic hydrogen, contributing their carbon to the chemical soup of the deep interior. We do not know for certain. No probe has ever descended into Saturn's interior. No instrument can directly observe conditions below the cloud tops. Everything we know about the deep structure of Saturn is inferred from gravity measurements, magnetic field observations, ring seismology, atmospheric composition, and laboratory experiments conducted at extreme conditions. The picture that emerges is extraordinary but incomplete. A planet with a fuzzy core of smeared rock and ice, surrounded by a deep layer of metallic hydrogen, where helium rains out and diamonds form, wrapped in a thick envelope of molecular hydrogen and helium that transitions seamlessly from liquid to gas. Saturn should not exist. Not in the neat, well-ordered way that textbooks describe planets. It is not a solid ball with a gaseous shell. It is a continuous gradient. A planet without a surface. A world where the interior is not a place, but a process. A constant churning of elements, transforming from one state to another, under conditions so extreme that the very definitions of solid, liquid, and gas become meaningless. And circling this impossible planet are 146 confirmed moons, worlds of ice and rock and mystery. Some are well known, many are barely studied, a few defy explanation entirely. Saturn's moon graveyard is a gallery of the strange, and it has stories that have never been properly told. Chapter 8. The Moon Graveyard. Saturn's 100, and 46 worlds, and the secrets they keep. Jupiter has 95 known moons. Neptune has 16. Uranus has 28. Saturn has 146, the most of any planet in the solar system. And that number keeps growing. As recently as 2023, astronomers using ground-based telescopes discovered dozens of new irregular moons orbiting Saturn. Tiny bodies just a few kilometers across, most of them captured asteroids or comets snagged by Saturn's gravity during the chaotic reshuffling of the early solar system. Most of these moons are unremarkable. Small, dark, irregular, tumbling through space on distant, tilted orbits. But among the 146, several are genuinely strange. Not just interesting, strange in ways that challenge fundamental assumptions about how moons form, how they behave, and what is possible in the outer solar system. We have already explored Titan and Enceladus, the two most famous. But Saturn's family runs deep, and some of its lesser-known members are among the most baffling objects in planetary science. Start with Mimas. Mimas is the innermost of Saturn's major moons, and the smallest object in the solar system known to have pulled itself into a roughly spherical shape under its own gravity. It is just under 400 kilometers in diameter. Its surface is ancient, battered, and almost entirely covered in impact craters. But one crater dominates everything else. Herschel crater, named after William Herschel, who discovered Mimas in 1789, is 130 kilometers across, nearly a third the diameter of the Moon itself. The impact that created it nearly destroyed Mimas. Had the impact been slightly larger or moving slightly faster, Mimas would have shattered. Herschel crater gives Mimas its famous resemblance to the Death Star from the Star Wars franchise, a comparison that was not lost on scientists when the first close-up images arrived. But the more interesting story about Mimas is not on its surface, it is inside. In 2024, analysis of Cassini data revealed that Mimas, like Enceladus, may harbor a subsurface ocean. The Moon's orbital libration, the slight wobble in its rotation, is larger than it should be if Mimas were a solid body of ice and rock. The best explanation is a global internal ocean, roughly 20 to 30 kilometers beneath the ice shell. This was shocking. Mimas shows no signs of geological activity, no fractures, no plumes, no resurfacing. Its ancient, heavily cratered surface suggests a world that has been geologically dead for billions of years, and yet the physics demands liquid water inside. If confirmed, Mimas would be the most unlikely ocean world in the solar system, a body that hides its ocean behind the facade of a dead, battered moon. Now, consider Hyperion. Hyperion is one of the strangest-looking objects ever photographed by a spacecraft. It is roughly 270 kilometers across, irregularly shaped, resembling a giant sponge or a piece of pumice stone. Its surface is covered in deep, sharp-edged craters with dark floors, giving it an appearance unlike any other body in the solar system. The craters are so deep and so closely packed that Hyperion looks like it has been eaten from within. The reason for this bizarre appearance is Hyperion's extremely low density, roughly half that of water. The Moon is likely a loose rubble pile of ice and void, more empty space than solid material. When meteoroids impact Hyperion, they compress the porous surface rather than excavating material, creating deep, sharp-walled pits rather than the broad, shallow craters seen on denser bodies. The dark material at the bottom of each crater is thought to be organic, rich debris that has settled into the lowest points. Hyperion's rotation is chaotic. Most moons in the solar system are tidally locked, always showing the same face to their parent planet, the way Earth's moon always shows us its near side. Hyperion tumbles. Its rotation axis wanders unpredictably from orbit to orbit, driven by the gravitational influence of Titan and the Moon's own irregular shape. This makes Hyperion one of only a handful of objects in the solar system with confirmed chaotic rotation. Predicting which face Hyperion will show to Saturn at any given moment is, in a rigorous mathematical sense, impossible. Then there is Iapetus. Iapetus was discovered by Giovanni Domenico Cassini in 1671, and it baffled him immediately. He noticed that the moon was visible only when it was on one side of Saturn. When it moved to the other side, it vanished. Cassini correctly deduced that one hemisphere of Iapetus must be much brighter than the other. He was right. Cassini the spacecraft confirmed and explained what Cassini the astronomer had observed. Iapetus has a striking two-toned appearance. Its leading hemisphere, the side that faces forward in its orbit, is coated in dark material as black as coal. Its trailing hemisphere is brilliantly white, as bright as fresh snow. The boundary between the two zones is sharp and dramatic. From space, Iapetus looks like a moon assembled from mismatched halves. The dark material is believed to be a thin veneer of organic, rich dust, swept up from Saturn's outer moon, Phoebe, and its associated Phoebe ring, a vast, tenuous ring of dark material orbiting Saturn in the opposite direction to most of its moons. As Iapetus orbits Saturn, it plows through this dust, accumulating it on its leading hemisphere, like a car driving through insects on a summer highway. Once the leading hemisphere darkens, it absorbs more sunlight and warms slightly. The warming causes ice to sublimate from the dark surface and redeposit on the cooler, brighter, trailing hemisphere, creating a positive feedback loop that sharpens the contrast over millions of years. But the strangest feature of Iapetus is not its color, it is its shape. Running along the equator of Iapetus is a mountain ridge, not a small ridge, a ridge that rises roughly 13 kilometers above the surrounding terrain, reaching heights comparable to the tallest mountains on Mars. This equatorial ridge extends for approximately 1,300 kilometers, roughly 3/4 of the way around the moon. It sits almost perfectly on the equator, like a seam on a tennis ball. No one fully understands how it formed. Several hypotheses have been proposed. Perhaps Iapetus once rotated much faster, and the ridge is a frozen bulge from when centrifugal force pushed material toward the equator before tidal interactions with Saturn slowed the moon's spin. Perhaps the ridge is the remains of a collapsed ring system that once orbited Iapetus itself, settling onto the surface along the equatorial plane. Perhaps it is a tectonic feature, a compression ridge formed when the moon's interior cooled and contracted. None of these explanations is fully satisfactory. The ridge remains one of the most enigmatic features in the solar system, a mountain range that has no business existing on a moon barely 1,500 kilometers in diameter. Saturn's smaller moons add further strangeness. Pan and Atlas, tiny moons orbiting within and near the edges of the rings, have distinctive flying saucer shapes, with pronounced equatorial ridges that make them look like ravioli. These ridges formed as ring material accumulated on the moon's equators, building outward grain by grain over millions of years. The moons are literally wearing skirts of ring particles. Daphnis, a moon just 8 kilometers across, orbits within the Keeler Gap in Saturn's A-ring. As it moves, its gravity creates visible waves in the ring material on either side of the gap. Ripples that propagate outward like the wake of a boat passing through still water. Cassini photographed these waves in exquisite detail, the tiny moon carving its signature into the ring with each orbit. Prometheus and Pandora, the shepherd moons, orbit on either side of Saturn's thin F-ring, their gravity confining the ring particles into a narrow band. Without these two moons, the F-ring would spread out and dissipate. They are gravitational herders, maintaining order in a system that would otherwise dissolve into chaos. Phoebe, orbiting far from Saturn on a retrograde orbit, moving in the opposite direction to the planet's rotation, is almost certainly a captured Kuiper Belt object. Its dark, irregular surface and unusual orbit mark it as a visitor from the outer solar system, trapped by Saturn's gravity during the early chaos described by the Nice model. Phoebe is a relic, a fossil from the primordial solar system, preserved in Saturn's gravitational embrace. Each of these moons tells a different story. Mimas hides an ocean behind a dead surface. Hyperion tumbles chaotically through space, its rotation unpredictable. Iapetus wears a mask of darkness on one face and carries a mountain range on its equator that defies explanation. Pan wears a skirt of ring particles. Daphnis carves waves in the rings. Phoebe is a captured refugee from the edge of the solar system. Together, they form a system so rich, so diverse, so full of unsolved puzzles that a single spacecraft spent 13 years exploring it and barely scratched the surface. That spacecraft was Cassini, and its story, from launch to death, is one of the greatest achievements in the history of human exploration. Chapter 9: Cassini, the greatest space mission ever flown. On October 15, 1997, a Titan IV-B rocket lifted off from Cape Canaveral, Florida, carrying a 6,800-kilogram spacecraft into the night sky. It was the heaviest interplanetary probe ever launched by NASA. Mounted atop it was a smaller craft built by the European Space Agency, designed to separate and descend to the surface of an alien world. The pair were named Cassini and Huygens after the two astronomers who, 3 centuries earlier, had made the first great discoveries about Saturn and its moons. The mission was a collaboration between NASA, ESA, and the Italian Space Agency. It cost roughly $3.2 billion over its lifetime, making it one of the most expensive robotic exploration missions ever undertaken. It carried 12 scientific instruments on the orbiter and 6 on the Huygens probe. Its power source was 73 pounds of plutonium-238, generating electricity through the decay of radioactive material. Because at Saturn's distance from the Sun, solar panels were impractical. The sunlight reaching Saturn is roughly 1% of what reaches Earth. Solar power was not an option. Cassini could not fly directly to Saturn. The planet was too far away, and the spacecraft too heavy for a direct trajectory with available rockets. Instead, mission planners designed one of the most complex flight paths in the history of spaceflight. Cassini performed 2 gravity-assist flybys of Venus, one of Earth and one of Jupiter, using the gravitational pull of each planet to gain speed and redirect its course. The journey took 6 years and 261 days. Cassini traveled roughly 2.2 billion miles before entering Saturn's orbit on June 30, 2004. The orbital insertion burn was one of the most nerve-wracking moments in the mission. Cassini had to fire its main engine for roughly 96 minutes, slowing down just enough for Saturn's gravity to capture it. If the burn failed or was even slightly off, the spacecraft would fly past Saturn and into deep space, lost forever. The burn succeeded. Cassini became the first spacecraft to orbit Saturn. What followed was 13 years of discovery that transformed our understanding of the Saturnian system. Cassini discovered the geysers of Enceladus. It confirmed the global ocean beneath the ice. It detected hydrothermal activity and the chemical ingredients necessary for life. It revealed the methane lakes and seas of Titan. It delivered the Huygens probe to Titan's surface, achieving the first landing in the outer solar system. It observed Saturn's hexagonal polar vortex in unprecedented detail. It watched the eruption and evolution of the 2010 Great White Spot. It measured the mass and composition of the rings with precision no previous mission had achieved. It discovered new moons. It photographed the rings in backlit glory, revealing structures invisible in any other lighting. It detected the tiny perturbations in the rings that proved Saturn's interior is fuzzy and sloshing. Cassini completed 294 orbits of Saturn. It performed 162 targeted flybys of Titan and 23 close encounters with Enceladus. It took nearly 500,000 images. Its data produced more than 4,000 scientific publications. By any measure, It was the most productive planetary orbiter mission in history. But all missions end, and the way Cassini ended is as remarkable as the mission itself. By 2017, Cassini had been in space for nearly 20 years. Its fuel supply, the hydrazine used to control its trajectory and orientation, was nearly exhausted. Without fuel, the spacecraft could not be steered. It would eventually drift on an uncontrolled orbit, and there was a real possibility that it could crash into Enceladus or Titan, two moons that Cassini's own discoveries had identified as potentially habitable. The problem was contamination. Cassini was not a sterile spacecraft. Despite precautions during construction, it carried terrestrial microorganisms, hitchhikers from Earth, embedded in its structure and instruments. If Cassini crashed uncontrolled into Enceladus, those microbes could contaminate the moon's ocean. If future missions then detected life on Enceladus, scientists would never know whether the life was native or whether it had been introduced by Cassini's impact. The scientific integrity of every future search for life in the Saturn system depended on keeping Cassini away from the habitable moons. The solution was elegant and devastating. Cassini would be directed into Saturn itself. The planet's thick atmosphere would incinerate the spacecraft like a meteor, destroying it completely and ensuring that no terrestrial contamination could reach any of the moons. This final phase of the mission was called the Grand Finale. The Grand Finale began in April of 2017, after a final close flyby of Titan on April 22nd. Titan's gravity bent Cassini's trajectory, launching the spacecraft over Saturn's rings and into a series of 22 orbits that passed through the gap between the innermost ring and the planet's cloud tops. No spacecraft had ever explored this region. The gap was roughly 1,200 miles wide. Cassini threaded it at speeds up to 70,000 miles per hour. Each of the 22 orbits brought new data. Cassini's instruments measured the composition of ring particles at close range. Its gravity instruments mapped the mass distribution of the rings and the planet with unprecedented precision. Its magnetometer sampled the magnetic field from closer than ever before. The data from these orbits alone would take years to fully analyze. During the final 5 orbits, Cassini dipped into Saturn's uppermost atmosphere, skimming through the thin gas at altitudes between roughly 1,000 and 1,060 miles above the cloud tops. The spacecraft's thrusters fired continuously to compensate for atmospheric drag, keeping the antenna pointed at Earth. These atmospheric skims were the first time any spacecraft had tasted Saturn's atmosphere directly. Cassini's ion and neutral mass spectrometer sampled the gas, measuring its composition in real time and sending the data home. On September 11, 2017, Cassini made a distant flyby of Titan. Mission controllers called it the goodbye kiss. The gravitational nudge from Titan trimmed Cassini's orbit one last time, bending its path to intersect Saturn's atmosphere on September 15th. There would be no more course corrections, no more flybys, no more escapes. The final day arrived. In the early morning hours of September 15th, Pacific Daylight Time, at NASA's Jet Propulsion Laboratory in Pasadena, California, engineers and scientists gathered in the Mission Control Center. Many of them had worked on Cassini for decades. Some had been involved since the mission's conception in the 1980s. They watched their screens. They monitored the signal. They waited. Cassini entered Saturn's atmosphere pointed at Earth, its antenna transmitting data continuously. 7 of its 12 instruments were active, collecting measurements of atmospheric composition, temperature, pressure, and magnetic field conditions. The spacecraft was falling at tens of thousands of miles per hour, plunging deeper with each second. As the atmosphere thickened, drag increased. Cassini's small thrusters fired harder and harder to keep the antenna pointed at Earth. The spacecraft fought to maintain contact. For about a minute, the thrusters held. Then the atmosphere overwhelmed them. Cassini began to tumble. The antenna swung away from Earth. The signal stopped. 83 minutes later, because that is how long it takes light to travel from Saturn to Earth. The silence reached the Deep Space Network's receiving station in Canberra, Australia. The signal, which had been streaming for 20 years, went flat. The mission was over. At JPL, there were tears, there was applause, there were hugs between colleagues who had spent careers working toward this moment and dreading it in equal measure. The project manager, Earl Mays, shook hands with the project scientist, Linda Spilker. The room was quiet for a long moment. Then it was not. Cassini was gone, vaporized in Saturn's atmosphere within seconds of losing contact. Its plutonium, its instruments, its cameras, its memory, all of it converted to heat and dispersed into the hydrogen and helium of the planet it had studied for 13 years. The spacecraft became part of Saturn. The New York Times ran the story on its front page. The Washington Post published an editorial with the headline, "The Cassini mission embodies the best of humanity." Google created a doodle on the day the grand finale orbits began. The hashtag Cassini trended worldwide. More than 3 million people visited the mission's website. For a few days, the world paused to mourn a robot and celebrate what it had achieved. Cassini proved that the outer solar system is not a frozen wasteland. It is a dynamic, chemically rich frontier where the conditions for life may exist right now. Not in some ancient past, not on some distant exoplanet, but on moons orbiting the 6th planet from our Sunday. It rewrote the science of planetary rings, atmospheric dynamics, moon formation, and astrobiology. It trained a generation of planetary scientists, and it demonstrated that when nations cooperate and commit resources to exploration, the rewards are immeasurable. But Cassini also left unfinished business, questions it could not answer, mysteries it uncovered but could not solve. And one of the deepest questions of all remains open. What happens next? Not just to Saturn's moons or its rings, but to the planet itself. Saturn is not eternal. Nothing is. And the future that awaits the ringed giant is both beautiful and heartbreaking. Chapter 10: The Dying King. Saturn's future and what the universe will look like without it. Saturn will outlive us. It will outlive our civilization, our species, probably our planet. A gas giant does not die quickly. It has no surface to erode, no atmosphere to lose to space, no internal fire that will burn out. Saturn will persist for billions of years, long after the sun has swollen into a red giant, engulfed the inner planets, and collapsed into a white dwarf. Saturn will still be there, orbiting the dim remnant of its star, cold and dark, but intact. And yet, Saturn is changing, right now, measurably, irreversibly. The most visible change is the one we have already discussed. The rings are disappearing. Ring rain is draining ice from the rings into Saturn's atmosphere at a rate that NASA describes as the worst-case scenario. Enough water to fill an Olympic swimming pool every 30 minutes. The Cassini spacecraft measured an even greater flow of material falling from the rings directly into Saturn's equator. Material that is not pulled along magnetic field lines but simply spirals inward under the combined influence of gravity and drag. Add both processes together and the numbers are stark. The rings may have less than 100 million years remaining. The innermost rings, the D ring and the C ring, will vanish first. The massive B ring will hold out longer, but not forever. The A ring, already losing material through the Cassini division and at its outer edge, will follow. Eventually, the only ring left will be the E ring, the one fed by Enceladus. And even that depends on how long the tiny moon can sustain its geological activity. Imagine Saturn without rings, stripped of the feature that makes it the most recognizable planet in the solar system. It would still be a gas giant, banded in gold and butterscotch, surrounded by moons, but it would look like a slightly smaller Jupiter. Anonymous, ordinary, the beauty that has inspired wonder for 400 years, from Galileo's confused sketches to Cassini's high-resolution portraits, would simply be gone. And the loss would be permanent. The conditions that created the rings, whatever catastrophic event destroyed one or two icy moons inside the Roche limit, are unlikely to repeat. The rings are a one-time gift, a transient ornament in the life of a planet that has existed for 4.5 billion years and will continue to exist for billions more. We are seeing Saturn during the brief window when it wears its crown. But the rings are not the only thing Saturn is losing. The helium rain inside the planet continues. Slowly, relentlessly, helium separates from hydrogen in the metallic layer and sinks toward the core. This process has been ongoing for billions of years and will continue for billions more. Over time, it changes the internal structure of the planet. The helium-enriched deep interior grows denser. The helium-depleted outer envelope grows lighter. The planet's thermal profile shifts. The magnetic field, influenced by the helium-insoluble layer, may change character over geological time. The diamonds, if they exist, continue to form and fall. Carbon from methane destruction drifts downward, accumulating in the deep interior. Over billions of years, this slow rain of gemstones may build significant deposits of carbon deep within the planet, altering the chemistry and density of the core region. Saturn's moons are changing too. Enceladus cannot sustain its geological activity indefinitely. The tidal heating that warms its interior comes from the gravitational interaction between Enceladus, Saturn, and the other moons, particularly Dione, with which Enceladus shares an orbital resonance. If that resonance shifts, if the moon's orbits evolve even slightly, the heating could decrease, the ocean could freeze, the geysers could stop. The E-ring would fade without its source. Enceladus would become what it appears to be from the outside, a dead world of ice. Titan's methane cycle faces a different kind of clock. The methane in Titan's atmosphere is slowly destroyed by ultraviolet radiation from the sun, broken apart into more complex hydrocarbons that settle to the surface. This photolysis is irreversible. Without a source to replenish it, Titan's atmospheric methane should be exhausted in a few tens of millions of years. If the methane is not being resupplied, possibly by cryovolcanic eruptions from the interior, Titan's atmosphere will gradually lose its greenhouse capacity. The moon will cool further, the methane rain will stop, the lakes and seas will evaporate or freeze. Titan's eerie, Earth-like weather cycle will shut down, leaving a cold, inert world beneath a thinning orange sky. Zoom out further. Billions of years from now, the Sun will evolve. It is currently a main sequence star, fusing hydrogen into helium in its core. In roughly 5 billion years, it will exhaust its hydrogen fuel and begin fusing helium. The Sun will expand enormously, becoming a red giant whose outer layers will reach roughly the orbit of Earth, possibly even Mars. Mercury and Venus will be consumed. Earth will likely be destroyed or rendered completely uninhabitable. Saturn, orbiting at 9.5 astronomical units, will survive the red giant phase. The Sun's increased luminosity will warm Saturn significantly, perhaps enough to alter its atmospheric chemistry and heat its moons. Titan might briefly experience temperatures closer to Earth's current range. The ice on Enceladus could melt more aggressively. For a cosmically brief period, the outer solar system might become more hospitable than the inner system has ever been. But it will not last. After the red giant phase, the Sun will shed its outer layers into space, forming a planetary nebula, a beautiful but transient shell of glowing gas. What remains will be a white dwarf, a dense, Earth-sized remnant of the Sun's core, slowly cooling over trillions of years. Saturn will continue to orbit this white dwarf, but with the Sun's mass reduced to roughly half its current value, Saturn's orbit will widen. The gravitational leash will loosen. Eventually, interactions with passing stars, gravitational perturbations accumulated over trillions of years, will alter Saturn's orbit. The planet might be ejected from the solar system entirely, becoming a rogue world drifting through interstellar space. or it might slowly spiral inward and eventually be consumed by the fading white dwarf. Or it might simply persist, orbiting the dead star in cold, silent stability for eons beyond human comprehension. We do not know which fate awaits Saturn. The timescales involved, trillions of years, are so vast that prediction becomes meaningless. What we do know is that everything we see today, the rings, the hexagon, the storms, the geysers of Enceladus, the methane seas of Titan, the diamond rain, the fuzzy core, all of it is temporary. All of it is a snapshot, a single frame in a story that stretches from the collapse of a dust cloud 4.5 billion years ago to the heat death of the universe itself. And in that single frame, we exist. We built a spacecraft. We sent it on a 7-year voyage across the solar system. We threaded it through the gap between a planet and its rings. We flew it through the geysers of a moon that might harbor life. We listened to its signal for 20 years. And then we watched it fall into the atmosphere of the planet it had studied, sending data until the very last second, becoming, in the end, part of the world it came to understand. Saturn does not care that we studied it. It does not know we exist. It is a ball of hydrogen and helium, spinning in the dark, obeying the same laws of physics that govern every atom in the universe. It has no purpose. It has no meaning beyond what we assign to it. And yet, when you look at Saturn through a telescope, even a small one, even for the first time, something happens. The rings resolve. The banding appears. A moon or two might be visible as tiny points of light. And you realize you are looking at something real. Not an image, not a rendering. A place, a world, a system of worlds, with oceans and storms and chemistry, and maybe, just maybe, life. Saturn is scary because it is magnificent and it is dying. The rings are falling. The storms are erupting and fading. The moons are ticking down on geological clocks we cannot rewind. The diamonds are sinking into darkness. Everything about Saturn is temporary, and everything about it is extraordinary. We are a species that had the intelligence and the ambition to build a machine, fly it 1 billion miles, and use it to discover that a tiny moon, 300 miles across, is shooting an ocean into space. We are a species that found a hexagon on a gas giant and spent decades trying to understand it. We are a species that measured ring, rain, and diamond precipitation and helium separation in the interior of a world we will never set foot on. And we are a species that, when the mission was over, when the fuel was spent, when there was nothing left to do, chose to destroy our own creation rather than risk contaminating a world that might hold life. That is what Saturn teaches us, not just about the universe, about ourselves. If you enjoyed this deep dive into Saturn and the mysteries of our solar system, please like this video and subscribe to the channel. Your support makes these detailed investigations possible. Tell me in the comments, which world should we explore next? Jupiter and its volcanic moon Io, the ice giants Uranus and Neptune, the sun itself and the storms that rage across its surface? Or perhaps a target farther away, an exoplanet where the conditions for life may be even more tantalizing than what Cassini found at Enceladus? Every world has its secrets. Every planet has its price. And every journey into the cosmos begins with the decision to look up and ask what is out there. Thank you for watching. I will see you in the next investigation.